Okay, now we got to get into torsion. All right, and the best, and I did watch some Whistling Diesel, actually, which is ridiculous. The guy is ridiculous. That was a waste of time, honestly, but it wasn't. Yeah, good point. But the best shaft, I think, that is most applicable to this class that I could think of, right, for torsion is a drive shaft in a vehicle, okay? For some of you guys that may not know, right, that's what transfers the force from our engine, from the transmission that comes from the engine into the drive train, okay? Axles, things like that, axle shafts into the wheels, and then propels us. As we get into electric vehicles, right, now we've just got electric motors on each of those four wheels, which still has a drive shaft, right? The shaft that drives the tires. So, what is a torque? Well, it's a moment that tends to twist a member about its longitudinal axis. Okay. And as I mentioned, an example of this would be a drive shaft. Okay. And in this class, we will cover torsion of shafts, and in particular, we're going to be looking at circular shafts, solid and hollow circular shafts. When you get into square shafts, like this, shit gets weird, okay? I'll put it that way, right? Torsional shafts, they behave very well as it relates to deformations, okay? This kind of shows you the grid and how this grid of lines displaces as the shaft torques or twists. When you get a square cross section, you get really weird stuff that happens at the corners where you get warping, and actually the shaft starts to displace in the axis of the shaft as you start twisting it, which gets weird, okay? So we're going to focus mainly on these two here. All right. Focus on circular shafts. Solid and hollow, okay? I did want to show you a few of these. Oops. What is going on here? Stop. So this is, why is this important? Well, really, this is fuck, that's a terrible picture. That one's better. That's a drive shaft that's failed due to excessive torsion, okay, or torque, right? This didn't fail due to yielding, it failed because of buckling. And we're gonna get into more circling, you're gonna realize that at a given angle, right, even though we're trying to twist this, and you could imagine it being like two planes shearing one another, well, if you orient that same piece of material at an angle, you're really trying to pull the steel apart and actually push it together. And so what will happen is, because we have these, drive shafts are very large diameter with thin cross sections, right? Because they're very good and efficient at transferring torque. But the unfortunate part about that is it can get so thin that it's unstable with respect to buckling. So it's going to be trying to pull it apart in one direction, but then it's actually trying to push it together. And the drive shaft will buckle and it'll start twisting like this. And we'll get into that when we talk about Moore's circle and transposing stresses and stresses at different planes. Another one is, holy shit, drill bits. Okay, I'm sure all of you guys have tried to drill a hole with a very small drill bit and that thing snaps off. Well, if you after you decided to throw the thing away, if you were to actually pick it up and look at it, okay, drill bits are very brittle because they're hard generally, and because they're very brittle, the drill bit will actually fail in a 45-degree angle spiral, which is neat. And it goes back to, again, those stresses at an angle. That drill bit is imposed with tension forces and compressive forces. Well, because it's a solid piece of material, it can handle the compression, but at a 45-degree angle to that compression force, there's a tension force, and it pops. So it spirally fails around its perimeter. Same as like if you took a piece of chalk, which I tried to find, which I'm sure was very easy one day up here at the university, hard to find right now. If you take just a piece of chalk, even sidewalk chalk, and you twist it in your hands, it's going to fail in a spiral. And that's because it's a very brittle material, and it actually pops apart at a 45-degree angle, because that's where our tension and compression forces are oriented, which is pretty neat. If you looked at a ductile, so this would be a brittle torsional failure of a solid shaft. When you get a material that's very ductile though, okay, it can handle the tensile forces. So like this is A36 steel. This would be like round stock you'd buy at Pacific, okay? It would fail in torsion where it would just shear off in a straight plane. And that's as we get into the mechanics of this, you'll know that the shear stress starts out maximum on the outside, and it'll build and build until it gets to the yield strength of the material. And as it gets to the yield strength, then after that it starts to yield, and it'll continue to yield and yield until it gets towards the center of the shaft. And then at some point it reaches the ultimate strain and ultimate stress of the material, and then it'll shear off. So you no longer with a ductile material get that brittle 45-degree angle kind of spiral failure that you do in like chalk. Okay? Pretty cool shit, I think. All right. So as with anything in mechanics, there's a sign convention, right? Because we do free body diagrams. That's how we understand internal forces. And so when we do free body diagrams, we need to understand a sign convention or have a sign convention. And so a positive torque is an outward normal. So what does that mean? If you use the right-hand rule like you do with a moment, right? Your thumb is oriented in the direction of outward from the face of this material, and you twist your fingers, right? The direction you're twisting your fingers is the direction of the torque, okay? So that would be a positive torque that faces outward. We use a double arrow to denote torque. So we looked at a 2D free body diagram of this. We'd have our double arrows. We'd have torque 1, say torque 2. We'd have our sign convention, right? Positive X to the right, positive Y up. And we could sum moments about the X direction, right? Typically, we've been summing moments in and out of the page, right? With 2D beam problems, right? And axial problems. Well, in this case, now we're going to be summing moments along the x-axis or along the plane of the page, okay? So if we did sum of the moments in the x direction, we set that equal to 0, right? We need equilibrium. We can't have this thing spinning off into space. So based on the coordinate system, right? T1 minus T2 has to equal 0. All right, so T1 equals T2. That's how we would go about a free body diagram.
So these torques will be given in like foot-pounds or newton-meters
Yep,
or whatever.
it's a moment essentially. It's a moment that's acting along the longitudinal axis of a shaft. Be a torque. So we have stress Or we have stress, we have strain, right? Deformation. So if we looked at a circular solid shaft that, say, was fixed on a wall or something, so if we grab this piece of rebar, right, and we set it on the wall and we fix it there, and we impose a torque on the end of it and we try and twist it, right, this torque T. As we go from the wall to the end of this shaft, right, it's going to twist, right? We're going to have a deformation at the end of the shaft. So that's what that phi is, right? That's this guy here. Without this torque, these lines would be straight, right? We impose a torque, now we start diverging those lines or rotating those lines about the axis of the shaft. Right, this torque is essentially this double arrow T, right? Positive outward normal. This would be a positive torque. If we assume this to be fixed, right? Attach it to something. We apply a positive torque. It rotates a given amount, right? Phi, a rotation of phi. Well, we want to look at this small section of shaft and look at what's going on in that little sliver of material. Okay, that's a delta X, or just a small portion of the total length, right? Well, if we looked at that small portion, okay, and we looked at our little square, without the applied torque, right, these angles would be 90 degrees to one another, right? We'd have a straight shaft. As we apply the torque and this thing deforms or rotates about its length, right, those angles no longer become 90 degrees. So we can look at that rotation, right, or that angular rotation of the cross section as we move down along the shaft as delta, right? This is angle of rotation. Or angle of twist. Okay. Its sign convention follows the positive right-hand rule. Okay, so this dashed line here would be a straight line. If we had no torque on this shaft, it wouldn't deform. We put a positive torque on it. It rotated downward, right, counterclockwise, which created this change in rotation, right, this angle of rotation of this small sliver of the overall shaft, right, and each one of them has this additional small amount of rotation, and it builds up as the shaft is longer and longer, right? So we have this angle of rotation or angle of twist, and it's positive downward because we have a positive torque on it. Right, so it's positive because it follows our right-hand rule for torque. This gamma is our shear strain. strain is a change in deformation over a change in length, right? Deformation over the original length. And so in this case, it is we have a linear increase in strain. Right? This line here, if we look at a very small sliver of the shaft, this line is linear as we go from one side of this sliver to the other. Right? This line here that goes the whole length of the shaft is linear. We have a linear increase in strain as we go across the section from, say, one end of the shaft to the other end, or one end of this little sliver to the other end of the little sliver, right? It's changing linearly from one side to the other. Well, remember, we've got Hooke's law, which we've discussed, right? That is from our tensile test. We've got this stress strain diagram, right, from our tensile test. We've got this stress strain diagram. It does something like this, where this was E, right? Our modulus of elasticity was the slope of this line, where we're in our linear elastic portion. Well, Hooke's law, we also made a relationship between shear stress, our shear modulus of elasticity, right, and our shear strain. Okay, did that earlier on in our class. And we know that our shear strain is our change in angle of rotation, right? It's our change in length, but in this case, because we're twisting, it's our change in angular rotation over the original length, right? That's the length of this sliver, or in our case, it could be the whole length of the shaft. One thing to note too, right? Because we have a torque that's acting along the longitudinal axis of our shaft, right? We've got this origin point, or zero, right? That's at the center of the shaft. And that point's not rotating, right? We get more and more rotation and more shear strain as we get further away from the center of our shaft. All right, so we have our change in angular rotation, or our angle of rotation is 0 at our origin. And we have our max rotation, or twist, at outside face. It linearly changes the amount of angular rotation as we go from the center of the shaft, which isn't rotating, to the outside of the shaft, which rotates the most. Right? So we get the most strain at the outside of the shaft. So if we now look at take this sliver, and now we look at the end of this sliver of shaft, okay? And we're looking at the stresses, the shear stresses that are acting at the end of the shaft, right? The origin stress is a function of strain, right? If we look up here, as strain increases, stress has to increase, right? Based on Hooke's law. So if the strain is 0 at the center of the cross-section, our stress is 0. If we have our max rotation or twist at the outside face, right? The angle of rotation, delta V over delta X, right? If we have our maximum delta T, that means our strain is going to be the maximum at the outside face. If our strain is the maximum at the outside face, our shear stress is going to be the maximum at the outside face. So it all comes back to Hooke's law relating stress and strain, where we've got tau equals the shear modulus times our shear strain. Basically saying if strain increases, linearly with radius, so does stress. So we'd get a cross section that looks something like this. All right, this would be looking at the end of our shaft as we induce a torque on this shaft. Right, we're going to induce strain in the shaft. Because we have strain, we're going to have stress. It's going to be 0 at the center because we don't have any strain at the center. As we work our way out, it's going to rotate more and more because we've rotated that shaft more and more as we go to the outside. We're going to get more and more stress until we get a maximum at the outside. So if we look at this, this is our radius C, right? That'd be the outside of our shaft. We've got this rho, and this is our distance to a point from center, okay? So rho could be 0. If rho is 0, we're looking at what's going on at the center of the shaft. If rho is C, well, now we're looking at what is going on at the outside of the shaft, right? So rho can be 0 up to C. If we look at what's going on here, knowing that we've got the maximum shear stress on the outside of the shaft and 0 at the inside of the shaft, right? If I wanted to know what the shear stress was at any given point, right, from the origin out to the outside of the shaft, knowing that strain varies linearly, if strain varies linearly from the center to the outside, then that means the shear stress varies linearly. If it varies linearly, we can just take the slope of that stress, the change in stress, right, which would be the rise, which is our maximum shear stress, over the run, which would be the radius, right? The slope times the distance. Well, the distance that we are looking at would be rho, right? So the shear stress at any given point from the center of our shaft to the outside of the shaft is the slope of that change in stress times the distance to where we are interested in looking, right? So tau at rho equals tau max over C times rho. We really want to come up with a way of relating our torque to shear stress, right? Because a lot of times we're going to be given torque. We're going to be able to develop a free body diagram and understand what internal forces are going in this shaft, right? And so we want to relate torque to shear stress. Well, we know force is stress times an area, right? Right? We want to get to torque. We're starting at stress. Well, I know stress times area gives us a force. And I also know that a moment is force times the distance, right? Or force times our moment arm. So if we know stress, we can get to an area, we can get to force. If we know the moment arm in which that force acts, we can get to moment. And the moment is essentially the torque, right? This is where you guys are going to black out because this is going to get into integrals here, okay? But if we were, just imagine you really enjoy this, okay? And we looked at a very small piece of this cross-section. Very, very small piece of this cross-section, okay? We said, I want to look at this small area that's going on right here. We're going to call it dA, right? Just a small area on this cross-section. And I want to know how much force is acting over that area, right? I would need to know the stress on that area and then the area itself, right? Force times area. Or stress times area, sorry, is force. So if we wanted to know what dF was, right, that would be this small force that's acting over this very small area on the cross-section. It would be the stress that's acting, right? So if we looked at an area that was rho away from the center, we know the stress at that distance is tau rho, which we know what that is. So we have tau rho times dA, right? Stress times an area. So we've got shear force and we've got stress at dA, right? That small little area of this cross section that we're looking at. Well, if we know if we have force, now we multiply that by a moment arm and we can get a moment, right? Which would be our torque. So if we look at the small amount of moment, or dm we would call it, that force dF is, right? How much force is this little area exerting on the whole cross section, right? So if we're looking at a small area, it's got a stress. So we multiply that area times the stress, we get a little force, right? A little F arrow. Call this dF. Right, we've got some small little dF that's acting right there. And that dF is acting at a moment arm. Well, if we're looking at the distance rho from the center, it's going to be rho dF, right? This was our arm. This is our force. And this is our moment. Well, now if we take our dF from over here and plug it in, we get dm equals rho the shear stress at rho times dA. Well, we know from up above that the shear stress at that distance rho is the maximum shear stress divided by the radius of our entire shaft times rho. So I'm going to substitute this big old guy here. So we're going to say rho times rho tau max over C times dA, right? So that is tau rho. We decided to plug in here. Well, the total torque or moment acting over the entire cross section, right, is all of these tiny little areas added up, right? All the forces that are acting over these tiny little areas based on the stress that's acting at these tiny little areas, you added them all up across the whole cross section, right? That's how much force is really trying to twist this. Well, in order to do that, this is where we get our lovely integral. That's what an integral is just summing areas. So we're going to sum the area over the expression we developed for a moment. We get this tau max over c times the integral of rho squared dA. Well, as engineers, we don't like to do integrals as much as you guys don't like to do integrals. So this rho squared dA essentially is a moment of inertia, but what they call it is a polar moment of inertia. Because no one wants to do the integral over the distance squared. And all the polar moment of inertia is your regular moment of inertia, right? Like we had I sub x, I sub y, right? In columns, we were looking at all of those moments of inertia. Well, the polar moment of inertia is just the resistance of twisting of a cross section, right? So you now have this axis that's running along the longitudinal direction. Well, this is calculating how stiff is your shaft with respect to rotation, right? The shaft's still going to have a moment of inertia, right? This direction as well as this direction, right? Or Ix and Iy, just like we had columns, right? This guy here must have fallen. Someone got, right? We had an Ix and an Iy. Well, this column also, this cross section has a polar moment of inertia. And how stiff is this thing from twisting about the centroid, right? So those are, a lot of those are always pre-calculated for us. Or we can, based on, we're dealing with solid circles and hollow circles, so we have equations to calculate those. So what do we do with polar moment of inertia? Well, the polar moment of inertia is deemed J. So what does that mean? Well, that means our force-stress relationship now says torque, right, which is our total torque or moment across the cross-section, is this tau max over c times this integral. Well, we decided that integral is now J. So really the torque on our cross-section is our maximum shear stress times the polar moment of inertia divided by the maximum radius of our shaft, right? A lot of times, though, we're given the maximum torque, right? And we really want to know what's the maximum stress. Well, you can rearrange this equation and say the torque on my cross-section times the radius of the cross-section, right? This is for circular or hollow shafts, divided by the polar moment of inertia is the maximum shear stress I'm going to see in the cross-section, right? Which, based on this cross-section, that maximum shear stress is going to be on the outside, right? Any questions there? Nothing? This is all just sitting in, feeling good. Right, T is torque, C is our max radius. Tau max is just that, it's the max shear stress. J is our new moment of inertia, polar moment of inertia. Which is essentially just how stiff is this shaft with respect to rotation about its longitudinal axis, right? Well, we can go back and say, sometimes we might want to know, what is the shear stress at any rho, right? Which is any radius. Well, that's just the torque, right? Because our maximum shear stress is on the outside, right? It's a linear relationship between shear stress and distance from the center of our shaft to the outside, right? So if I wanted to know what the shear stress was at any given point within the cross section, we could just substitute in rho for our max radius, right? So we're looking at any given radius from the center, and we can figure out what our shear stress is. Right, those are some big equations to note. They're also on that big equation sheet. Right? Can't stress that enough. That equation sheet is very useful. So as I mentioned, we are dealing with circular shafts, whether they're solid or hollow. And we don't like to do things twice as engineers. Someone has already figured this out. Polar second moment of inertia, or moment of area is really what it's called. Okay. It's inches to the fourth, millimeters to the fourth. It's going to be in, if we look at a solid circle, they've done the integral already, right? The integral of rho squared dA over the area. We have a circular cross section, or oval like that one. And it's got a radius r, a diameter d. Our polar moment of inertia is simply pi over 2 times the radius to the fourth, which is the same as saying pi over 32 times the diameter to the fourth. Okay. So if you know the dimensions of your shaft, the diameter or the radius, you could calculate your polar moment of inertia. If you have a hollow circular shaft, or kind of oval like that one, you're going to have a small r and a big R, small d and a big D dimension, okay? Small denotes the dimensions for the inner circle, right, or the void area. The big letters, right, big R and big D are the dimensions to the outside of our circle, right? The outside of the shaft. If that's the case, they give us our polar moment of inertia is pi over 2 times r to the fourth minus little r to the fourth. You can imagine very similar to the solid shaft, except for now we're just taking out that void material. Similarly with diameter, okay? With diameter, we've got big D to the fourth minus little d to the fourth times pi over 32. Same with in our axial problems, right? We really wanted to figure out this relationship between force and deformation. Right, that was very helpful. If you remember for axial, it was this delta equals FL over AE, right? And that came from Hooke's law, and then substituting in force over area is stress, right? And strain is change in length over the total length. Well, that's exactly what we're going to do here. We're going to say similar to axial deformation. Right, we've got this delta is FL over AE. We're going to start with Hooke's law. That tells us that stress is our modulus, shear modulus, times our shear strain. Well, we know from previous notes, I keep writing P, but it's not P, it's rho. The shear stress, right? The shear stress at a given radius is the torque times the radius, where we are interested in knowing the shear stress, over the polar moment of inertia, right? We also know that our shear strain is our radius times our angle of twist per unit length. That's what this is. Well, if we plug all of those things in, we multiply by the length, right? Because this is angle of twist per unit length. So if we took d phi over dx and multiplied by the length, we would get our total rotation, right? Our angle of rotation. So we'd get our angular rotation phi equals the torque times the length over g, whoops, not L, J. This is unitless. So this is our force deformation relationship. How much has the cross-section rotated? Well, how much that value is dependent on the amount of torque that's applied, the length of the shaft, your modulus, your shear modulus, okay, of elasticity, and your polar moment of inertia, right? How stiff is your cross-section to rotation? Right? Very similar to our PL over AE, right? This would be an important one, okay? This equation, though, is only valid for constant G. If your shear modulus changes, right? Essentially saying your material changes, then your rotation angle is going to change, right, as you go across the length, because the material properties of the shaft are going to change, so your stiffness is going to change. We also need constant internal torque. Right? We can't have a varying torque load as we go down the shaft. We've got to have discrete torques applied on our shaft so that from one place to another, our torque on the inside of the shaft is constant. Also needs to be prismatic. Our shaft needs to be, so that means the diameter and the polar moment of inertia are constant. The diameter of the polar moment of inertia changes, the stiffness changes, right? And that screws up the linear behavior that we've assumed from the very beginning, that our stress is going to change linearly as we go from the inside to the outside. Our change in rotation is linear as we go down the length of the shaft, right? These lines, we assume, make these nice straight lines as we go down along the shaft as this thing rotates, okay? we start changing any of those parameters, it screws all of this up, okay? So we're going to keep it simple, and that's what we're going to assume. We can also derive, based on some of the other equations that we've already derived for shear stress, okay, and angle of rotation, we can derive 3 more equations that are helpful. The angle of rotation is also a function of the shear strain times the length over the distance we are looking at, okay, from the center. We can also say shear stress at a given radius times the length over that radius times the shear modulus also gives us our angle of rotation. And then finally, our maximum shear stress times the length. So you can imagine we now have C times the shear modulus, also the angle of rotation. All of this assumes a linear relationship, as I mentioned, so those will all work. But by far the one we'll use the most is the one that's highlighted there, which relates torque, the length, the shear modulus, and our polar moment of inertia to the deformation of our shaft, right? The rotation of it. All right, we're gonna go through an example and you'll see how straightforward this is once you know the equations, okay? Derivation was the hardest part of this whole thing. So if we had a hollow stainless steel shaft, so essentially a pipe, okay? It has a shear modulus of 86 gigapascals. It has an outside diameter of 42 millimeters and a wall thickness of 4 millimeters. Has an allowable shear stress of 100 megapascals. They want us to determine 2 things. They want us to determine what's the maximum torque that may be applied to the shaft. Well, if they gave us an allowable shear stress, you can imagine we're going to limit our torque based on hitting that shear stress. And then they want to know what's the angular deflection at the max torque if the rod was 1.75 meters long. All right, so if we have a shaft, wow. Try to do better here. Better. Okay, they said it is 42 millimeters in diameter. It said the wall thickness was 4 millimeters. And they want us to figure out what is the max torque that may be applied to the shaft. Well, if we look at our big equations, right, we have our maximum shear stress of the cross section is the torque times the maximum radius divided by our polar moment of inertia. And we also have our angular deformation is torque times the length over the shear modulus times the polar moment of inertia, right? Those are our 2 big equations. Well, we're calculating what the maximum torque is. Well, we can take our first equation, right, which relates the maximum shear stress to the torque, rearrange it, so now we get maximum torque is our maximum shear stress times J all over our radius, right? Our maximum radius for our cross section. Well, if we go through this equation, polar moment inertia, well, we've gone through some equations to develop that for a hollow shaft. Maximum shear stress, right, acts at the maximum radius. Well, in this case, they told us that the allowable shear stress, or the stress that we can not exceed, is 100 megapascals. So they essentially are limiting our maximum shear stress, which is going to limit our torque. And then they also give us our max radius as, right, 42 divided by 2, which would be 21 millimeters. So we have that also. So we've got everything here. We just need to calculate our polar moment of inertia. Well, that was, I'm going to go with diameters. So I'm going to say for a hollow shaft, it's pi over 32. Large diameter, small diameter to the fourth. So pi over 32 times 42 millimeters to the fourth minus 34 millimeters to the fourth, right? That would be 42 minus 8. We get a J equal to 174,296 millimeters to the fourth. We also need our max radius, C. Well, that's just the diameter over 2, right? The big diameter. So 42 millimeters divided by 2 equals 21 millimeters. And they gave us 100 megapascals. So we can start by saying maximum torque equals our allowable shear stress, which was 100 megapascals. Well, remember that's Newton per millimeter squared is a megapascal. Our J, 174,296 millimeters to the fourth, all over max radius of 21 millimeters. All of the millimeters cancel except for one. I'll just cancel this, cancel that. So we get a max torque equal to 829,980 Newton millimeters, right? This is a torque or a moment. Or our max torque is 830, Newton meters. And on Wednesday, we'll come back and finish part 2. Pretty straightforward, right? Got our 2 big equations. We calculate our maximum torque based on our allowable shear stress for the first time.
For the first time.
Yeah.